All right, any questions with our shorthand notation? Going to save us a lot of time by using that. No? Okay. Now, on Friday we said that the periodic table is kind of like your best friend. It gives you lots of answers. It makes a lot of correct predictions when you follow the flow of it, but it's not perfect. And there's actually some exceptions to what you would predict for the electron configuration. And we'll just write them out. Chromium, palladium, and tungsten, those three elements are exceptions. And notice on the periodic table that chromium, palladium, and tungsten are all in the same column right here, group number 6 on the periodic table. Another group with exceptions on the periodic table would be our copper, silver, and gold, which is group number 11. These don't follow the rules off of the periodic table that you would predict. So those are 6 elements that we have to know for the test. Trust me, you're going to get some of these guys on that test on Friday. So first let's look at what the wrong answer is, because that's going to help us understand what the right answer is. So what you would predict for chromium, and we'll actually write out the whole electron configuration for our chromium, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And we'll just look at that right. Actually, if we did our shorthand, it would just be argon, and then you'd have 4s2, 3d4. So here's our argon, and then you'd have 4s2, and then remember when we get to the D sublevel, we subtract 1 from the row number for the energy level, so that'd be 3d1, 3d2, 3d3, 3d4, and that's what you'd predict. However, this is incorrect. And then one would ask the question, well, why, and what is the right answer? Well, the correct answer is actually this. It's the electron configuration for argon, and then it's 4s1, 3d5. Now, if you look at this, remember this superscript number here, that's the number of electrons. What is 2 plus 4? It's 6. What's 1 plus 5? It's 6. So this, what you predicted compared to what the correct answer is, aren't the number of electrons the same? Chromium has got 24 protons, 24 electrons. It's got 24 electrons in it. So we didn't change the number of electrons when we said, hey, this is the right answer. All we did is we moved an electron from the 4s energy level and sublevel into the 3d. There was this shift right here. And now the question is, well, why is it acceptable to have this shift? And why does it occur? And we really need to give our next rule, and that is this. Energy sublevels, and we're going to want to write this in our notes, are stable when they are filled up with electrons. So for the S sublevel, that would mean when it looks like S2. What would that mean for the P? What does the P hold at maximum? 6. What about the D? 10. The F? Whoops. That would mean F14. So let's think about this as it relates to, I don't know, let's look at neon. Neon's electron configuration would be 1s2, 2s2, 2p6. What do we notice about all these energy sublevels? They're all filled up. Okay. Now, something like fluorine, on the other hand, 1s2, 2s2, 2p5, fluorine is a very, very reactive element, and the reason being is because when you look at the 2p5, it is not filled up with electrons. Atoms want to become stable by filling up their sublevels with electrons. As it turns out, and we're going to want to write this down, sublevels are somewhat stable when they are half filled. And then the question becomes, well, what would that look like? That would be like S1 or P what? P3. For D, that would be what? D5. And for F, that would be F7. Now, when we go back over here, what would we label for our incorrect answer? What would we label the 4s2? Stable, somewhat stable, or unstable?
Stable.
It's actually very stable. By the way, everything else is unstable for the sublevels. So if you're filled up, you're really, really stable. If you're half filled up, you're somewhat stable. Everything else is not stable. So the 4s2 would be very stable. What can we say about the 3d4?
Unstable.
It's very unstable. And if we go over here, what do you know about the 4s1?
Stable.
It's somewhat stable. What do we know about the 3d5?
Unstable.
Somewhat stable. So, as it turns out, this is the more apt structure for the chromium because you've got more stability here than what you've got up here. And by the way, you might say, well, Mr. Gartrell, how come you can actually have that electron go from here to here? That's because the 4s and the 3d energy levels are very close to each other. The energy gap between them, the packet of energy to go from here to here is very small. And just that little bit of extra energy gives you that added stability. And here's a good analogy. One would say, why is this what you get rather than this? So let's say, I told you, because I was going to go ahead and build a house. And I made the house out of masking tape and cardboard. Well, what's going to happen when it rains? And we get wind and those types of things, and snow. It's going to turn mushy, the cardboard will absorb that, it's going to fall apart. Unstable structures fall apart. What happens with stable structures? They last a long time. I would argue that the pyramids are a very, very stable structure. By the way, the Great Pyramid at Khufu is 400 and I believe like 81 feet tall. To this day, it's still the tallest stone structure on the planet. All the tall skyscrapers we have, they're made out of what? Steel. Okay. So if you're a really stable structure, you stay around. That's why this is the correct electron configuration for chromium, because it is stable. Does that make sense to us? Now, we said that palladium and tungsten basically follow what? They follow the same rule. They're an exception. So let's go ahead and do this. If we want to write down the electron configuration for palladium, what would be our abbreviation that we want to write down? Here it is here, palladium, atomic number 42. We'd use krypton, Kr. Put that in brackets and then build up. So after 36 comes 37. So you would predict 5s2, and then you'd predict 4d, 1, 2, 3, 4. And guess what? This is not correct. Again, what happens is an electron from the 5s is actually in the 4d. So the correct answer is this, 5s1, 4d5. And notice that the correct electron configuration here for palladium is really the same thing as the chromium, except now we're talking about higher energy levels here. Does that make sense? By the way, why does it make sense that all these guys were +2? Because wouldn't they all be S2s? S2, 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 S2. So they're all going to have the tendency to lose 2 electrons to end up looking like a noble gas. So that's why when you look at elements that are in the same column, they have similar reactivities and similar chemical properties. And you've been taught that in the lower grades, yes? Elements in the same family have similar chemical properties. What you might not have known is why. It's because they really do have the same structure. It's just the energy levels are further out. But they got the same number of electrons that are involved in bonding. For example, if we're to go ahead and do fluorine, fluorine's electron configuration is 1s2, 2s2, 2p5. So how many valence electrons for fluorine? What's the highest energy level? It's n equals 2, isn't it? What's 2 plus 5? 7. So fluorine has 7 valence electrons that would be involved in bonding. If we look at chlorine, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. What's the highest energy level for chlorine? It's n equals 3. How many electrons does it have that are valence? 2 plus 5 is 7 valence electrons. That's why fluorine and chlorine are both going to have very similar reactivities. Matter of fact, we did that reactivity of halide ions. Notice that we formed precipitates and things were very similar in those columns for things. This is linked up with that. Everything that we do in here is connected together.
It's just a movement in that one with the 5 feet unstable.
Yeah, this is rather interesting. A lot of the times students will say, well, you're moving the electrons around here to make things stable. How come that doesn't do the same thing for other elements? And we can take an example. We might as well, if you want to, take our chlorine. If you look at chlorine, what would you guys say about the 1s2? Stable or unstable or somewhat stable?
Stable.
Very, very, very stable. What about this, 2s2? Very stable. What about the 2p6? Very stable. What about the 3s2? Very stable. What about the 3p5?
Very stable.
Very unstable. Because it's not filled up and it's not half filled. Now, somebody says, well, let's make it 1s2, 2s2, 2p6, 3s1, 3p6. You say, I'm going to go ahead and move an electron. Well, this guy would still be really, really stable. Actually, all these would right here because they're the same thing, right? Very stable, very stable, very stable. Now, when you compare 3s1 to 3s2, who's more stable? This is more stable. This is only somewhat stable. And when you compare 3p6 to 3p5, yeah, this is very stable. And then one would say, why doesn't this happen? Well, these guys are actually in the same energy level. You're really only getting the shift when you have your 4s and your 3d when the energy levels are different. This, they're in the same energy level, so you don't get that shift. Okay. And even if you tried it with the iron, you would find out, let's say for iron, that it wouldn't work. Now, let's take a look at our other three, our copper, our silver, and our gold. We'll take a look at copper. What are we going to write down for our brackets to save ourselves time? Copper's right here. We're going to write down argon. And we're going to build up after that. After 18 comes 19. So we'll say 4s2. Then you'd say 3d 1, 2, 3, 4, 5, 6, 7, 8, 9. And this ends up being incorrect. Remember, very, very stable, very unstable. So what we end up getting for copper is we end up getting a shift. It's 4s1, 3d10. Notice that this is very, very stable, and this is somewhat stable. And very, very stable and somewhat stable is going to be stable, very unstable. So this would be the electronic configuration for copper. Now, what would the silver look like? The silver is basically going to be the